Hi, everybody. So what I'd like to do in this lecture is to do our test 2 review. This is for Physics 2020, spring of 2022. So let me get started. I'll share my screen. All right. So here we go. Now, in general, the format's going to be real similar to the last test. You can bring in a 3-inch by 5-inch index card with equations, just like last time. And we're going to cover chapters 3, 4, and 6 in Purcell and Morin. There's a little bit of coverage of chapter 10 on the dielectrics for capacitance, which is from chapter 10 in Purcell and Morin. Now, the coverage in our matter and interactions textbook is a little happier, smilier in terms of their wording and their equations. It's true. But one of the things that I find a little strange or frustrating about matter and interactions is that the order of things is kind of strange to me. So I follow the order of Purcell and Morin, but occasionally drop down the level of difficulty to match matter and interactions in this, just so you know. Now, there's some sections in chapters 3, 4, and 6 that we're going to skip. For example, we're not covering the vector potential stuff, which is in chapter 6, section 3. And our coverage of the transformation in electric and magnetic fields, I'm only doing the non-relativistic stuff. The E and B transformation in Purcell and Morin's in chapter 5, but we're skipping that entirely because it's all special relativity, so we're not doing that. So what I did was I scanned in a few pages from an alternative text and placed it underneath the lecture. I tried to, underneath each one of the online lectures that I created, create a little line where I say what sections of what text they're done in. Okay, so if you want the matter and interactions coverage, then I'll do it there. But bear in mind that some of the sections, matter and interactions doesn't cover it all. So there you have it. Okay, starting off with chapter 3, we began talking about capacitors, and capacitors are charge and energy storage devices. The capacitance of an object, C, can be written in terms of the charge stored on the capacitor and the voltage of the capacitor. So C is equal to Q over V is the equation for capacitance. The SI unit of capacitance is the farad, and 1 farad is equal to 1 coulomb per volt. Now, just like the coulomb, 1 farad is actually an enormous unit. And so usually you'll find microfarads to picofarads to be typical capacitances of things that you might solder into a circuit. Now, although C is equal to Q over delta V, you'll see when you solve for the capacitance of an object that it just depends on the geometry of the object. Okay, more about that in a second. Now, you'll need to review how we found the capacitance of capacitors of symmetric shapes, like nested spheres, nested cylinders, or parallel planes, okay? Now, how we did this in each case was that we found the electric field between the two objects, either between the two parallel planes or between inside sphere and outside sphere, for example. We found the electric field between them, usually via Gauss's law, because we only solved the capacitance for highly symmetric situations. And then once we had the electric field, we found the voltage from the electric field. Remember that the relationship of the voltage to the electric field is something that you need to burn into your brain. And that delta V is going to be equal to minus E dot ds. So it's a line integral from plate 1 to plate 2, in other words. And then you're going to plug that into the formula C is equal to Q over delta V to find the capacitance C. One that it might be worthwhile to just remember or write down on your card is the equation for the capacitance of a parallel plate capacitor. And that capacitance C is equal to epsilon naught A over D. Remember that epsilon naught is the permittivity of free space. It's a fundamental constant, 8.854 times 10 to the minus 12 in SI units. A is the area of the plate, and then D is the spacing between the plates. So you can see here that the capacitance, like I said, is dependent upon the geometry, just the area of the plate and the plate separation, and then a fundamental constant, and that gives you that. Now, we can also find the energy stored on a capacitor, and we derive that equation as the potential energy stored on a capacitor is equal to 1/2 the charge on that capacitor times the voltage in between the plates, 1/2 Q delta V. And then you can use the equation for the capacitance, C is equal to Q over delta V, and to put it in 2 other forms. Okay, now, if you have capacitors in a circuit and you have more than one, and you'd like to find the equivalent capacitance for that circuit, and there's no other resistors or anything like that in there, okay? So you're just looking at capacitors either in series or in parallel with one another. Then if you've got capacitors in parallel, then you find the total capacitance by adding up the capacitances of the capacitors in parallel. So C para is equal to C1 plus C2, for example, but you'd keep going if you had more. Now, if they're in series, then what you do to find the equivalent capacitance is to, I'm sorry, this should be C series. You do 1 over the equivalent capacitance for a series, 1 over C series is equal to 1 over C1 plus 1 over C2. So the reciprocal of the equivalent capacitance is the sum of the reciprocals. Now, one of the exercises that we did in practice was to find the voltage drop and the charge and energy stored on capacitors in a circuit with just a battery and multiple capacitors. So make sure that you review those and you can do those types of problems. Remember, the basic strategy is to find the total equivalent capacitance for the circuit. And then you find the charge stored on that equivalent capacitor, which would be like if you just had a battery and one big old capacitor, right? Now, remember that the charge stored on capacitors in series is always going to be the same. So if you find the equivalent capacitance for the circuit, and then there's capacitors that are in series with the battery, then that equivalent capacitance charge stored will be the same as those capacitors. Also remember that the voltage drop over capacitors in parallel is the same, and the voltage drop for capacitors in series add. And so the total voltage drop for the circuit has to equal the voltage of the battery that they're hooked up to. So all of those things, you can kind of just break it down step by step and use that to find the charge stored and the voltage dropped over each capacitor in the circuit. And then remember that via C is equal to Q over delta V, that if you have either the charge or the voltage, then you have the other. And then with one of those two things and the capacitance of the circuit or capacitance of the capacitor, you can also find the energy stored on that capacitor. Okay, so just practice that. We did some example problems in class and some for homework. Now remember that if you have a parallel plate capacitor, for example, with nothing in between it, that your equation for the capacitance is epsilon naught A over D. But if you stick something in between the plates of capacitor, like an insulator, then that's called a dielectric, okay? Now, dielectrics will increase the capacitance of the capacitor by an amount known as the dielectric constant kappa. The dielectric constant is a ratio of the permeability of the substance that you stick in there, the permeability of your insulator, divided by the permeability of free space epsilon naught, 8.854 times 10 to the minus 12, and that's SI units. Okay, so dielectrics increase the capacitance of capacitors. So they also, though, provide mechanical support for the capacitor, and that helps keep it from shorting out, keeps the plates from touching. So they have a lot of advantages. One thing also that you need to remember is that when you put a dielectric in there, it reduces the total electric field between the capacitor plates by the dielectric constant. So E is equal to the field without the dielectric in there, epsilon naught divided by kappa, the dielectric constant, okay? Now, oftentimes, dielectrics are rated by the max electric field that the material can withstand before it breaks down and sparks. This is a material property. Okay, and so that will be the max electric field strength. Okay, so that might be something that's given to you, like for a particular material. Now, how dielectrics work is they store charge on the surfaces of the material. The charge is also stored for that capacitor on the capacitor's metal plates. And the charge stored on the capacitor is called the bound charge. And the density of the bound charge on the surface of the dielectric is related to the density of the charge on the surface of the capacitor via the formula sigma induced is equal to sigma naught times 1 minus 1 over kappa, the dielectric constant. So if you need a review of any of these things, just remember you can look back at that online lecture. Now, remember that if you place a material in a strong electric field, that what that will do is cause within each atom or molecule, for example, charge separation. In other words, you will induce a dipole, an electric dipole in the atoms or molecules of the material. That ability to do that, how easy it is to create those dipoles, is called the polarizability of the material. okay? And it's often symbolized by the vector symbol capital P. So the polarizability is the average dipole moment per unit volume that you get in the presence of an electric field. And it depends on the material properties. Specifically, if you can measure the dielectric constant of material kappa, then the polarizability P will be equal to epsilon naught times the electric field you apply times kappa minus 1. So to summarize what happens, here we have depicted a little parallel plate capacitor with a positive charge here on the left and a negative charge built up here on the right. That creates an electric field E naught within the material, okay? And so when you have that externally applied electric field, here our insulating material, our dielectric is represented by this, yellow box, okay? So you can see that the material inside becomes polarized. You can see the little dipole moments form. The dipole moments are induced, and then they rotate to align with that external field. And that creates a net dipole moment per unit volume in the material, or polarization. And that polarization causes an electric field in the material that's opposite to the externally applied field, which reduces the net field in the material by the dielectric constant, okay? And also, the alignment of the dipoles within the material causes a surface charge. Even though this material itself has no net charge, you can see that on the surfaces, you're going to get a net negative charge there on the left and a net positive charge on the right, just due to the way that the little dipoles are oriented. Okay, so that's where that bound charge, that surface charge, comes from. Okay, chapter 4. We talked about current. We defined current as the amount of charge that passes some reference point per unit time. Okay, so you would measure a current by counting up the number of charge carriers that pass that reference point, multiplying by the charge of each charge carrier, and then dividing by your time interval. If you're looking at the average current, that would be I average is equal to delta Q over delta T. But then if you shrink down to a small time interval delta T, then you can write it as the instantaneous current, I is equal to dq dt. Now, we talked about a model of conduction. It's a semi-classical model. I guess I should say semi-classical model, known as the Drude model of conduction. And so what this says is that each atom in a metal, usually they're metals, contribute a free electron, one or more free electrons to the free electron C. How many free electrons each atom contributes depends upon the electronic structure, which depends upon which atom it is. But on average, it's 1, okay? So each atom contributes about 1 electron to the free electron C. And then that electron is free to move around, kind of like an ideal gas molecule. It just zings around, okay? Now, because there's defects in the material and because the electron can run into a lot of stuff, it doesn't have a nice straight line path when an electric field is applied. Instead, it'll have a crazy zigzaggy path, okay? So when an electric field is applied, the charge carriers feel a force due to that field, which is due to the applied voltage, of course, and that force is F is equal to QE. Now, since the charge carriers are usually low mass, the accelerations are usually very high, but they're prevented from getting to a very fast speed because of all the collisions that they undergo. And so on average, they will drift along with a relatively low velocity, given the size of the acceleration, due to all the collisions. Okay, so that's what the model is. Okay, now these electrons are always zigzagging and running around, but without an externally applied electric field, there's no net motion. They'll zig left just as often as they zig right, for example. Now, we derived the equation for the current from the Drude model of conduction. I'm not going to repeat that derivation here, but I will remind you of the equation. The current I in a conductor, a metal, is equal to NQA times V sub D. Now here I is the current, of course, in amps. N is the density of charge carriers. So it's the number of charge carriers per unit volume in the material. Remember that you can derive that from the density of the material, the molar mass, and knowing the number of electrons donated per atom, okay? So remember how to do that. Q is the charge per charge carrier, right? Usually plus or minus the electronic charge, 1.602 times 10 to the minus 19 coulombs. Most of the time, right? That's what you're going to have. A is the cross-sectional area of your wire or whatever else you're looking at, right? So here, the cross-sectional area for a cylindrical wire would be a circle, Okay, that's pretty typical for these types of things. And then the drift velocity V sub D is how fast on average those charge carriers move. Okay. Okay, make sure that you can apply this equation, make sure that you know how to solve for N from the density of the material. We did this in some example problems in class and also on the homework. Okay, we defined the current density. The current, as you saw from that equation for the Drude model for conduction, is dependent upon the wire that carries it. If you have a fatter wire, for example, you can have more current, but that's a little annoying, right? We'd like to have equations that don't depend upon the geometry of the objects in question. And so what we end up doing is defining the current density, which is the current per cross-sectional area I over A. Now, in one form of Ohm's law, the current density is proportional to the electric field. Remember that electric current is a vector, it goes one way or another through the wire, for example, so that's a vector. J is also a vector, and it points in the direction of positive charge flow, okay? And J is equal to sigma E, and the electric field E is also a vector, okay? Sigma here is the conductivity. The conductivity is a material property. It's going to change from material to material. That should be obvious from your basic experience. Some materials are more conductive than others. Remember that your conductivity, sigma, is also proportional to the resistivity. They're flip sides of one another. So sigma is equal to 1 over rho, where rho is the resistivity. Oftentimes, in fact, we report our values of the conductivity in terms of, the resistivity rho, and we just do the units flipped. Now, the conductivity, we derived this equation in class, for the material is equal to NQ squared tau over M. Now here, N is that charge carrier density that I talked about on the previous slide. Q is the charge per charge carrier. Tau is the mean free time, which is the average time between collisions in the material. And M is the mass of the charge carrier, okay? Also remember that we derived the resistance, big R, of a current carrying object. That resistance was equal to rho L over A, where rho is the resistivity of the material, L is the length of the object, and A is the cross-sectional area. And so you can see that the resistance increases as the object gets larger, right, longer, and it decreases as the object gets fatter. And I like to think of that like I think of water through a pipe, right? So there's going to be resistance to the water flow through the pipe if it's a long, skinny pipe, but there's not going to be much resistance to the flow if it's a short, fat pipe, right? Now, from this value for the resistance, R is equal to rho L over A, and our equation, Ohm's law, J is equal to sigma E, we can derive another form of Ohm's law, which is probably one that you're more familiar with. Delta V is equal to IR. So the voltage drop across a resistor, for example, is equal to the current flowing through the resistor times its resistance R. Remember that the SI unit of the resistance is ohms. We reviewed the three types of materials: conductors, insulators, and semiconductors. Remember that Ohm's law, which I talked about on the previous slide, is only valid for ohmic materials, which are usually the metals and not the semiconductors, okay, or the insulators. So talking about that, we already talked about the Drude model for conduction, which covers conductors. Insulators and semiconductors are different. They have what's called a band gap. Okay, and the band gap, what you have to do is you have to apply a certain amount of energy to that material in order to create a free electron. In a metal, the free electrons are just there and they're already free. But in semiconductors and in insulators, you have to give it energy to free that electron. In an insulator, it takes about 10 electron volts to free it. And in a semiconductor, it's about 1 electron volt. And that's my physicist hand-waving order of magnitude value there. It's going to differ from material to material, okay? But that's the order of magnitude. Okay, semiconductors, those valence electrons, which is those outer shell electrons, it's relatively easy to promote them to the conduction band. And so often that's done by heat or a small applied voltage. And in an insulator, it takes a lot more energy to get that to happen. Now, if you have an ohmic material in electrical circuits, the rate at which work is done, power, can be described by the equation power is equal to the current times the voltage. And then you can use Ohm's law, second form, V is equal to IR, to get that power equation in different forms. P is equal to I squared R, P is equal to V squared over R, for example. Now, we also talked about how to handle resistors in a circuit, okay? If you have multiple resistors and you wish to find the equivalent resistance, then you add up the resistance to find the equivalent resistance if they're in series, okay? And if they're in parallel, then you take the reciprocal of the equivalent resistance to get the sum of the reciprocals, gives you the reciprocal of the equivalent resistance if they're in parallel, okay? Make sure that just like the capacitor problems, that you can find the power dissipated in a resistor and the voltage drop across resistors in those problems. Okay, so we talked about how to deal with circuits that have a bunch of capacitors and a battery, and we talked about how to deal with circuits that have a bunch of resistors and a battery. But if you have multiple batteries or crazy thing going on in your circuit with different kinds of components, then you need a new strategy. And that strategy is Kirchhoff's rules, okay? So there's two rules that we go by. It's the loop rule and the junction rule. Junction rule first. The junction rule just says that current that flows into a junction has to equal the current that flows out of a junction, okay? This is really just a restatement of conservation of charge. So usually what happens is you have, for example, one wire branching off into two wires, and the current into I1 is equal to the sum of the currents out, I2 plus I3. But this would hold for however many wires go in and come out of a junction. Now, Kirchhoff's loop rule says that if you go in a complete closed loop around a circuit, then the sum of the voltage changes across all the components has to add up to 0. And this is just a restatement of conservation of energy ultimately, because remember that potential energy and voltage are related to one another just by multiplying the charge. So when you say that the voltages must sum to 0 in a closed loop, it's the same thing as saying that the energy can't be any different from the starting to the ending point of a loop, okay? Energy is conserved. Make sure that you can do problems with Kirchhoff's rules. We did a bunch of them. We did a bunch of them in class and for quiz questions and homework questions. Make sure that you review all those and you understand them. The next thing that we covered in circuits was RC circuit. So this was when you had both resistors and capacitors in a circuit. Then you need your RC circuit equations. So let's say that you have a charging capacitor. What happens is that, and a resistor, what happens is that you throw the switch, for example, at time t is equal to 0, the capacitor is initially uncharged. And then the resistor is kind of restricting the flow of current, so it keeps it a little slower, right? But eventually charge builds up on the plates of the capacitor. Now, it does this exponentially, so it's an increasing exponential function. That's what the charge on the capacitor is described by. So saying that mathematically, the charge on the capacitor as a function of time, Q of t, is equal to Q max times 1 minus e to the minus t over RC. Q max is the maximum charge that would be stored on that capacitor if you let the circuit go forever, okay? RC is the resistance times the capacitance of the components there, the resistance and the capacitor. And if you multiply those together, RC has units of time, and it's called the time constant of the circuit. It's often symbolized by the Greek letter tau. Now, if instead you want to look at what's happening to an RC circuit where you have a charged capacitor and it's bleeding off that charge through a resistor, no battery this time, then what's going to happen is that charge will leave the capacitor plates and flow through that resistor, and it will decrease exponentially. And so Q of t in that case is equal to Q max times e to the minus t over RC. That's just a straight up exponential decay. And again, Q max would be the charge on the capacitor when the switch is first closed, so it's its maximum charge. Now remember that for either of these equations, I is equal to dq dt. And so you can find the current, okay, by just taking the derivative of that charge equation. So for a charging capacitor, I of t will be equal to the EMF of the battery that it's hooked up to divided by R times e to the minus t over RC. That means that for a charging RC circuit, what you have is initially your current is very large, and then the current gets smaller and smaller the longer it runs. For a discharging capacitor, it will be an exponential decay too. The current is going to be described by I of t is equal to minus Q over RC, e to the minus T over RC. And that minus sign, all that is it just says that the current is flowing away from the positive plate when the capacitor is discharging. And that's opposite to the direction that usually flows for a charging circuit. For a charging capacitor, the current flows positive charges away from the battery and building up on the positive plate of the capacitor. But when it's discharging, it goes the other way. Okay, that pretty much sums up the high points of chapter 4. Next, we moved into chapter 6. Remember, we skipped chapter 5. And this is information about magnetic fields, okay? So magnetic fields, first of all, what are their units? The SI unit of the magnetic field is called the Tesla. Yet again, a Tesla is an enormous unit. A more useful unit is the Gauss. There's about 10 to the 4th Gauss in a Tesla. Okay, 2 Tesla can pick up a car. MRIs are 10 Tesla, but the Earth's magnetic field is 50 microtesla, depending on where you are. Magnetic fields can be caused by currents, moving charges, changing electric fields, and magnetic materials. Of course, the magnetic material, like the ferromagnetic materials, at its root is still just moving charges. It's just on the atomic level. Okay. So we went through a whole segment on how to find magnetic fields for various configurations. We began with what's called the Biot-Savart law. Remember that magnetic fields can be caused by currents or moving charges. The Biot-Savart law describes, first of all, how a moving charge particle can create a magnetic field. The Biot-Savart law for a moving point charge is mu naught over 4 pi times QV cross R hat over R squared. Here, mu naught is another fundamental constant. It's called the permeability of free space, as opposed to the permittivity of free space, epsilon naught. And mu naught is 4 pi times 10 to the minus 7 Tesla meters per amps. So that's the SI units. Now, Q here is the charge. V is the velocity vector for that charge, so the direction it's moving. R is the vector that points from the moving charge to the point of interest where you want to know that magnetic field. R hat is the unit vector that points in that direction, okay? So the magnetic field for a moving charge particle is given by the right-hand rule. And remember that in general, what you can do is you can figure out, for example, if you take your thumb of your right hand and point it in the direction of Q times V, then your magnetic field around that will make loops, okay? And the loops will be in the direction that your fingers naturally curl. Now, this is a vector cross product, okay? So make sure that you practice your vector cross products. Make sure that you know how to do those, okay? Remember that if you're doing A cross B, the magnitude of the vector cross product is AB sine of theta, okay? So it's proportional to the sine of the angle. Also remember how to take a vector cross product with a 3x3 determinant method. That's really important, okay? There's a lot of cross products here. Now, if you have a bunch of moving charges, of course you have a current. So that's another form of the Biot-Savart law. Here, the little differential element dB for a section of current, like a length of wire ds. dB is mu naught over 4 pi times I ds cross R hat over R squared. Here, of course, I is the current, ds is a little segment, and the rest of it's the same as before. Now, if you want the total magnetic field, what you would do is, of course, integrate that over the wire in question at the point of interest, okay? And we did some examples on how to do that in class, and you did some for homework. Now, don't confuse this field with any field that might be there that's external to the conductor. This is the magnetic field created by the current carrying wire, all right? Also remember, the current is defined as the direction of positive charge flow. Thank you, Ben Franklin, right? Most of our charge carriers and wires are electrons, which means that they're going to flow the other way, but the current still points in the direction like a positive charge would move. Now, this Biot-Savart law is good for equations that break symmetry. So if you have something that is not a highly symmetric situation, you'll need to use the Biot-Savart law to find the magnetic field, okay? If it is a highly symmetric situation, like a solenoid or a toroid or something like that, then a better way to do it would be Ampere's law, which we'll cover in a minute. Okay, we had some fundamental laws that we talked about. Remember that magnets and magnetic fields, sources of magnetic fields, don't really come in monopole form, okay? So anytime you have a magnetic material or an atom or whatever else, you're going to have closed loops for magnetic fields, okay? So this means that if you put a Gaussian surface around a magnet, that the magnetic field that goes out of the Gaussian surface has got to circle around and come back in, which means that the net magnetic flux for a closed surface is going to be 0. And that's because there's no magnetic monopoles, okay? We haven't found any particles yet that have by themselves a North Pole, for example, or a South Pole. Even though there's nothing necessarily forbidding that from happening, Dirac postulated the existence of magnetic monopoles, but we haven't found one yet, a single particle. Okay, Ampere's law. Oh, right. So this is the, integral form of Gauss's law, the integral about the closed surface, B dot dA is equal to 0. And then remember that we also used our vector calculus to derive the differential form of Gauss's law for magnetism. And that is that the gradient dotted with the magnetic field is equal to 0, which is a way of saying that magnetic fields don't diverge, right? Okay, here's Ampere's law. Ampere's law states that the line integral of the magnetic field about a closed loop, the integral of B dot ds about the closed loop, is going to be proportional to the current enclosed by that loop, okay? So the integral of B dot ds about the closed loop is equal to mu naught times I enclosed, okay? Now, if you're not enclosing the whole current, okay, then you can find I enclosed by integrating J dot dA, the current density, over the area of your Amperian loop. Now remember that when you apply Ampere's law, there's a lot of similarities to Gauss's law, but one thing that's different is that it's not a closed surface, okay? Your Amperian loop is going to be an open surface, right? Like here we show a circle, so it's not a sphere, it's a circle, it's an open surface. Remember that you want to choose your Amperian loop such that every point along the way, your magnetic field is parallel to the loop, or is perpendicular to the loop, or there's no magnetic field there. So you want the dot product, in other words, to give you either 0 or 1 for the cosine theta term. And if it doesn't, don't use Ampere's law. You can use the Biot-Savart law and do just as good a job in solving the magnetic field, and it won't be nearly as confusing, okay? So for example, for the long straight wire, the Amperian loop that we defined was walking in the same direction that the magnetic field encircles the wire, like so, along that green line. And then you can tell that since it's equidistant from the center of the green line, that the magnitude of the magnetic field every step along the way will be the same. So you can pull the B out of the integral, right? And also that B and your path, B and ds here, are parallel at every point along the way. So that cosine theta term from the dot product is 1, okay? So that's how you do that. Okay, now in its differential form, which we derived in another, using vector calculus in another lecture, Ampere's law can be stated that the gradient cross B is equal to mu naught times J. So this is the curl of B is equal to mu naught J. And basically what that's saying is that magnetic fields, the sources of magnetic fields are currents, and the magnetic fields from these currents that are created by these currents will encircle the current, okay? You should know and be able to derive magnetic fields for the following geometries: long straight wires, outside or inside, okay? Current loops in the center of the loop, we used Biot-Savart law for that. Long straight wires, Ampere's law is probably your best bet. Solenoids and toroids, the best bet for finding those is Ampere's law, because those are highly symmetrical situations. Remember that a solenoid is basically a cylinder with a wire wrapped around it very tightly, and that solenoids are useful because they generate very strong straight magnetic fields in the interior along the long axis of that cylinder. Toroids, remember, are just donuts, so it's a donut solenoid, okay? And they also generate nice strong magnetic fields in the interior that encircle the in the inside of the donut, okay? All right, so that's magnetic fields. Now let's talk about the forces that fields exert on charged particles, okay? Now we already knew from previous studies that the force from an electric field on a charge was F is equal to Q times E. But now we're adding on and we're getting the full Lorentz force law. And the full Lorentz force law says that the force on a charged particle in an electromagnetic field is equal to QE plus QV cross B, okay? Now the implications here are that electric fields exert forces on all charged particles, whether they're moving or not. But magnetic fields, the charge must be moving in order to exert a force, okay? Now, for magnetic fields, the force will be exerted in a direction dictated by the right-hand rule, okay? So make sure you know your right-hand rule. And in this situation, for example, where we have a uniform magnetic field into the screen, okay, and we have a charged particle there, but no electric field, you can see that in this case, the charged particle entered the magnetic field moving at right angles to the field, and that caused a force inward towards the center of this circle here. So basically, if you have a uniform magnetic field and you have a velocity at right angles to that field, then your charged particle will make circles in that magnetic field. Now, in this case, remember, centripetal force isn't a force in and of itself. Centripetal force is always provided by something else. So what we can do is set the magnitude of the centripetal force here, mv squared over r, is equal to the magnitude of the force from the Lorentz force law, QVB, okay? Now here, since V and B are at right angles to one another, that sine of theta term goes to 1. So what we can do is write the magnitude of the force, QVB, equals mv squared over r. And then we can solve, for example, for the radius, right? And the radius of that circular path will be mv over QB. You can also, on the flip side, measure the radius of a moving charged particle in a magnetic field. And if you know its speed, use that to determine Q over M, the charge to mass ratio. And this is how mass spectrometers work, at least some of them. Now, this is what happens when you have a charged particle whose velocity is at right angles to the field. But in general, of course, you might not get such a perfect setup. You might have a charged particle entering a magnetic field and it has components both parallel and perpendicular to that external field. In that case, it's not going to make a circle, it'll make a helix. So the part that of the velocity vector that's perpendicular to the field will cause it to circle, and the part that's parallel will be undisturbed, and so it will continue along that path, resulting in the helical path that you see here, okay? And we did an example problem in class for the helix, so make sure that you look over that and you understand. The next thing that we covered was the Hall effect. The Hall effect discusses a current carrying conductor placed in a magnetic field. So here, for example, we have this, I guess, rectangular solid, okay, shown here in blue, this little rectangle there. And there's a current flowing I to the right. And the magnetic field in this region is into the screen, okay? Now, what would happen here is that there's going to be a force on those moving charged particles which make up the current. And that force will be given by the right-hand rule, F is equal to QV cross B. Now, what'll happen is that will cause the charged particles to move perpendicular to their direction of motion. So it'll give them an acceleration either up or down, depending on the sign of the particle. So for example, if in this case, you have your charge carriers are positive, as is shown here, then the force QV cross B on those charged particles will be upwards, and your positively charged particles will build up on the top part of your conductor. If you have the charged particles being positive charge carriers, then that would leave an absence of positive charge on the bottom, and so you have this separation of charge that happens in your current carrying device. Okay, what that does is it creates a voltage in between the top and the bottom of your charge carrier. That voltage creates a field. That field would cause a further force on those moving charged particles. So what will happen is the charge will build up until the electric field that's created counteracts the magnetic field force, and then charged particles from that point on can move through undisturbed. So the charges will build up until the maximum possible voltage is reached, which is called the Hall voltage, okay? Delta V sub H is shown here. Now that Hall voltage is when the electric and magnetic field forces balance, and that is easily shown to be the drift velocity of your charge carriers times the magnetic field times the width d of the conductor here. That's the top to bottom width d, and then that's equal to the electric field times d. So that's your Hall voltage. With a little bit of extra work, you can derive the following equation, that the Hall voltage delta V sub h is equal to J over NQ times BD, okay? And this just comes from the Drude model for conduction equation. Remember, J is your current density, I over A. N is your charge carrier density, and Q is your charge. Okay, the last thing that we covered, and is the last thing that's going to appear on this test, is that electric and magnetic fields are really flip sides of the same coin, okay? If we just do a simple transformation from a stationary to a moving frame, and here I'm not even talking special relativity, I'm talking slow speeds, and I'm talking inertial frames of reference that are moving along at constant velocities. So it's a Galilean transformation. It's very straightforward. If you do a simple transformation from a stationary frame to a moving frame, then you can see that electric and magnetic fields, what looks like a magnetic field in one frame will look like an electric field in the other. Now, the way that we write these transformations, I'm not going to go through the full thing, that's already done online. So if you need a review of that, please look back at that. But the equations which relate the magnetic and electric fields from the moving or prime frame to the magnetic or electric fields from the stationary frame are as follows. The magnetic field in the moving frame, B prime, is going to equal the magnetic field in the stationary frame, B, minus 1 over c squared times the velocity, the relative velocity of the frames, which you could call either V or U, whatever you want, crossed with the electric field in the stationary frame, E. Now, the electric field in the moving frame, E prime, is equal to the electric field in the stationary frame, E, plus the relative velocity of the frames, V or U, cross B. Okay, so that's how you relate those two things. Now, in our homework, this can be very mind-bending. So we didn't get too much past just straightforward application of this, okay? And so that would be what I would expect from you on the test. Now, sometimes you can write, you can see here that there's a 1 over c squared right there. And sometimes that is written as, instead of 1 over c squared, as minus mu naught times epsilon naught. Now, we haven't really covered this too much yet, okay? We'll really punch this in Maxwell's equations when we get to that and when we get to light. But it's fun to note that the speed of light c in a vacuum is actually equal to 1 over the square root of mu naught times epsilon naught, which is the multiplication of those two fundamental constants, 4 pi times 10 to the minus 7, or 8.854 times 10 to the minus 12 in SI units. Okay, so that sums it up. That's all she wrote. That's all of it. I know it's a lot, okay, but I have confidence in you. I think you can do it. Just remember that if you forget everything else, please remember how to do a cross product. There's so many cross products once you start getting into magnetism. And so it's really important that you know how to do those. Here's some resources for you if you need a review on how to do any of that. Don't forget, the best way to learn physics is to practice by doing more problems. Don't forget that your Purcell and Morin textbook, where is it? Has a chapter 12, okay? And chapter 12 in Purcell and Morin gives you worked examples for all the exercises in the beginning part of each of those chapters. So if you want more problems to do on the stuff that we covered, that's one place to look at it. Another good place to look at it is the example problems in your Matter and Interactions textbook and the example problems in Purcell and Morin. Also, don't forget, we're going to do a practice test in class. I'll also post that practice test online, okay? And you'll be able to get some practice using that. Okay. See you in class. Bye.